This is going to be a very brief skim over the top. There's not going to be much to back up what I'm going to tell you. In other words, I'm not going to be able to do the derivations. For that, you're going to have to read the books, but we are going to hit all the important issues as we go through, and all the important things that I think you'll want to know about. If you want more detail, that'll have to come from the books. We can't do that in a weekend. When we do the introductions today, it'll take us right up to the point where we're starting to get serious about the content. Okay, we're kind of going to get you primed, and then more of the content will be delivered on Saturday and Sunday. Saturday is going to be about the theory of reality. It's going to be how does it all work? What is it? How does it work? Who are you? How are you connected to the system? What does it mean to you? The whole fundamental notion of what is existence about and why and how. That's what I call the theory. So we're going to do the theory Saturday. It's going to start out slow, and then we're going to pick up the speed, and by the time we get to the last hour or two on Saturday, you'll probably be dizzy. We'll be going pretty quickly. The concepts are simple to say. They're hard to get at a deep level. That's because they're going to break a lot of your paradigms, a lot of the ways you're used to thinking, a lot of your, what I call cultural beliefs, just things you believe just because you do, just because it's in your culture. Those things are at a very deep level, and they're hard to get around, and you'll be struggling with those as we go. Now Sunday, we're going to change the pace altogether, and we're going to talk about the larger reality. How do you get into it? What are you going to find there? What can you do there? You know, what are the skills that you'll need in that larger reality? And at the end of each of the days, Saturday and Sunday, we're going to do some kind of hands-on experiential exercises where I'm going to give you some techniques about how to heal, how to diagnose, remote view, and we're going to experiment with a few of those things. And it's not that you're going to end up being wizards at the end of the weekend, but you should have the techniques that allow you to do these things and practice them and know kind of what you're doing with it. And those will also break some of your paradigm. I'm sure some of you already do those things, but this will be probably very different than what you're used to doing. Okay, before we get any further, I would like to thank Donna Aveni Warner and Keith Warner. They're the two sitting back here in the back. They've put all of this together. They have single-handedly created MBT events. They've funded it, organized it, all the workshops. You know, everything that came together today to make this possible, they're responsible for doing it. And they did all of that for the promise and actuality of absolutely nothing other than my lasting gratitude. So Keith and Donna, thank you very much for making this possible. All right. Some of you know who I am and kind of know my background. Some of you probably heard more of it than you want to because it's on YouTube, and all of the talks I give, it has that up in the front, but there's always 20, 30% that have no idea. They kind of wandered in here by mistake, and they're not really sure who is this guy and where does he come from. Well, now and always a scientist is a good way to describe me. I majored in physics and mathematics in college, went on to graduate school, did my thesis research in experimental nuclear. I now work as a consultant. I've been working just up until the last week with NASA. I'm changing jobs, going to pick up someone with MDA and one with SMDC, two government organizations in Huntsville. What I do there is risk analysis. And that's what I do in all these places. That seems to have been the last major thing I ended up doing. You know, careers are funny. You never know exactly you know, what your career is going to be until you're in it. But it seems that I've wandered into risk analysis, and what that is we make models, what's called physics models. They're very accurate models, mathematical models of very complex systems in order to determine what those systems will do, what's the probability that they'll do that? And if it's a problem, how do you fix it? So the risk analysis, we're looking at risks, the things that could go wrong in big systems. And then hopefully designing the system so it doesn't go wrong, or if it does go wrong, having a plan B to fix it. That's basically what I do. So I'm a working physicist, not in an academic sense, but in a industry sense. Okay, so how did I come to write books about consciousness? Usually physics and consciousness don't necessarily go together. You don't have a lot of physicists talking about their big toes. Well, when I was at work for maybe only a few months, my boss, Bill Yost, he introduced me to Bob Monroe's first book, Journeys Out of the Body. Now at that time, that was Bob's only book. This is now 1972, very early in 1972. And he had read the book, wanted my opinion on it, and handed me the book and said, Tom, read this and tell me what you think. Well, I did read it, and I don't know how many of you are familiar with Bob Monroe's Journeys Out of the Body, but probably a lot of you are aware of it and know it. And like most books like that, I read it, and I said, well, I told my boss when he asked me, what did you think? I said, there's three things, three possibilities here. One, this guy has a really good imagination, and he's trying to sell books. He's just making all this stuff up. Two, he thinks all this happened, but he's just nuts. All this is just going on in his head. He's having nightmares and dreams. And then three is he experienced it just the way he said he did. It's real. The experiments that he said he did, he actually did do. And there's a whole lot of reality that I didn't know anything about. And being a physicist, that's my game, is to understand and model reality. That's what I was interested in. So I was real interested in finding out whether it was 1, 2, or 3. But it's one of those, how do you know? It's a book. How do you know where this guy's coming from? Well, it wasn't that long before I got an invitation to go out to meet Bob Monroe. As it turns out, he lived only about 45 minutes from where we worked, and a group arranged to go out and see him. And we did, and I found out right away that it wasn't 1 or 2. As the car pulled in this long, about mile-long driveway, the first thing you noticed was the whiteboard fence and the horses running alongside with the cars. And you figure this is now like a 500-acre estate, with 2 lakes, big house on the hill, this sort of thing. And it's like, well, Bob didn't need to sell books. Certainly not books about out of body. The man was well-to-do. And that wasn't it. So then I met him, and he was a very genuine, very warm, very straightforward. He had nothing to sell. He wasn't trying to convince anybody of anything. He just wanted to understand what had happened to him. He wanted it to be real. He didn't want to be the crazy guy that had funny things happen. He wanted it to be legitimate. He wanted it to be science. So we found out at the end of the day why it was he had invited us out there. We stayed the whole evening with him, probably about 4 hours. And at the end of the day, we were all sitting on the deck behind what was called the lab. It was one of those prefab homes that you build on the spot, or maybe even wheel in on the spot. Dennis calls it a trailer. It was sort of like that, but glorified trailer. And had this deck on behind it. And we were sitting out there, and Bob looked at us. We were all from, at that time, an organization called the Foreign Science and Technology Center. And we were all scientists. And he looked at us and said, well, you guys are all engineers and scientists, right? And we kind of said, yeah, wondering what was coming next. And then he said, well, would any of you be willing to come here and help me set up this lab, build equipment, and study consciousness? And it took me just a millisecond to get my hand in the air and say, yes, I'd love to do that, but I want you to tell me what you know about out of body. Teach me what you know. And then just a few seconds later, Dennis Menerick, who was a double E, I'm a physicist, he was a double E, so we kind of rounded out the science pretty well. He put his hand in the air and said, yeah, I'd like to do that too if you teach me what you know about out of body. So Bob thought about it. He was looking for some older, more distinguished scientists with reputations and so on that could help his cause, but he had to settle for a couple of, late 20s, almost 30 young guys like Dennis and I. And Dennis, by the way, is here with us today. He's sitting in the back. That started a very long process for Dennis and I going out to Bob Monroe's Mondays, Wednesdays, and Fridays. We'd go out there. We'd get there after dinner, maybe 6:30, maybe 7. We'd work in the lab, build the equipment, try to turn it into a real lab. Then Bob would come up. We'd go get in the beds. There were these 3 booths that were there that were isolated. They were electromagnetically isolated, and they were acoustically isolated from each other. And we go lie down in those beds, and Bob, we'd had earphones on, and he would then teach us to communicate with him while he was teaching us to go out of body and to get into altered states. We had to talk to him at the same time so that he would know what we were doing. I mean, it was hard to teach somebody something that you don't really know what they're experiencing. So that was the arrangement. That was a little odd at the time to be able to be in those kind of altered states and still carry on a conversation, but you learned to do it. My technique was to have the experience come back, sort of bifurcate, if you will, be there, be here at the same time. So part of me was still there, part of me was here, and you kind of learned to parallel process that way. That was the way I did that. So Dennis and I then, we spent the next 5 years putting in about 25 hours a week out at the lab with Bob Monroe, working on creating the lab and on learning to go out of body. Well, after about a year and a half or 2 years of that, we had pretty well come to the conclusion that what we were doing was very unusual. We were keeping statistics on everything. We were reading numbers on blackboards. We were healing people. We were remote viewing. We were doing everything we could that was evidential, that you could find out later whether or not you actually were doing it or not. We were looking at headlines in newspapers a week in advance. We would go remote view and then find out what was going on at that place at the time we were remote viewing, and so on. So we had gotten to the point where we were going out of body pretty much at will when we wanted to, and it didn't take us more than probably about a year and a half to get to that, but it takes a different kind of experience to convince you that this is real. That can't be an intellectual experience. Up to that time, it was all intellectual. Yes, we'd gone places, we'd met people, we'd done things, and the probability that what we had done was just chance, like the healing or the remote viewing, well, that was probably 1 in 100,000, 1 in a million. We were getting fairly good with practice at getting right answers at that sort of thing. But still, that's all in your intellect. It wasn't until Dennis and I did an out-of-body trip together that it hit me at a personal level that this was real. And we took a trip together. We met in the air above the lab, went off on an excursion together. It was probably an hour and a half, 2 hours worth of tripping them around in the larger consciousness system. We talked to each other, we saw things, and when we came back, Bob had that all recorded, of course, from our voices on those 2 independent tapes. And Dennis and I, of course, couldn't hear each other. We were completely isolated. So we came out of that room, walked up to the control room, and Bob was there, and he played the tapes for us. And he loaded both the tapes, and he flipped the switches at the same time. You had Dennis and I talking to each other, responding to each other, seeing the same things, the same descriptions, something that was just impossible to do if you hadn't done it. And that was the one that hit me at a deep level. And I think after that, it took me a few weeks to kind of get over the idea that it's real. Up until that point, it was just strange and fun. And okay, the statistics were 1 in a million, but it's not real until you have that sort of an experience. So that was kind of how I got here. And then after that time, being a physicist, what I was interested in was, how does it work? What are the limits? What can you do with it? What does it mean? If it's a reality, then it's like this reality. It's got its own physics. It's got its own causality. It's got its own reasons why it exists. So that was my mission then for the next 30 years, was to find answers to those questions. And the way you do that is with research. You have to go into those reality frames and do things to the point where you can repeat them, and it's science, and you know what you're doing, do experiments and find out what's the causality. How does it work? And it takes a long time. About 35 years later, I thought I finally got the aha moment. I kind of understood where, what was going on and how it was going on, and that's what led me to My Big Toe. And I started writing that. Actually, the very last book, book 3, is what I wrote first, and I passed it around, and most people shook their heads and couldn't really get it. Actually, it started as a much smaller version of that. So I'd ask them what their problem was, and they'd tell me what they were hung up with, and I'd write more. And I'd pass that out, and people would tell me what they didn't understand, and I'd write more. And pretty soon, I either had one giant book or I had a trilogy. So that's the way the books actually went together. It started with book 3, and then book 1 and book 2 are kind of an on-ramp, so that by the time you get to book 3, you have a good probability of understanding what's there. And then, of course, book 1 and book 2 took a life of their own as far as they had their own content to spread. But that's kind of how it was written. It was written with a lot of help from a lot of people, some of which I've never met face to face. And these were people all over the internet. The internet's a wonderful thing. And people who were interested. I would say, oh, you're interested in this subject? Here, read this and tell me what you think, and they would tell me, oh, that doesn't make sense, and here's why. So then I'd fix it. So if you wonder why it sounds like I'm talking to you when you read those books, it's in that kind of chatty, personal tone, that's because that's the way it was written. I was writing to answer people's problems. So if it appears to you that it just happens to be talking to you when you read it, you think a question and then in the next paragraph there's the answer, that's why, because that's the way the book was written, to answer people's questions. So that's the nature of it. Okay, one thing about out of body is because I got my start with Bob Monroe, oftentimes people see me as kind of Mr. Out of Body, or maybe a Mr. Out of Body 2, if you will. Bob's probably the original Mr. Out of Body. And that's not what it's about. Okay, this is not about the out of body experience. It's so much bigger than that. This is about, who you are, what you and reality have to do with each other, why you're here, how does it work? That's what's more important. If you focus on what I call the phenomena, like out of body, any of the paranormal experiences, if that's your focus, you'll probably just end up frustrated. That's not the right place to start. Now that's an attractive pull. That's like the pretty flower to the bee, right? That attracts a lot of people to this idea because they want to, oh, that would be neat. I'd like to go out of body. I'd like to be able to heal. I'd like to be able to remote view. So it kind of brings people in, but it's a mistake to make that your focus, your point of being involved in it. Your point in being involved in it ought to be to grow up, to drop fear, drop ego, increase the quality of your consciousness, and you'll find out later what all those terms mean. If you do grow up, those things just fall out, you see. They're natural. They're easy if you want to put just a little effort to refine them. So don't get the cart in front of the horse. Grow up first, then all the paranormal things will just fall into place as you need them, as you want them, rather than focusing on the paranormal things and not on growing up, you'll be frustrated. All right. The first thing I like to do is calibrate my audience. So you're about to be calibrated. It won't hurt. I'm going to break many of your favorite paradigms over the next 2 days. I'm going to run over a few of your most cherished beliefs, personal beliefs, cultural beliefs. And I want you to remain skeptical and open-minded. If you're not skeptical, you run the risk of believing whatever I tell you. That would not be good. If you're not open-minded, you run the risk of not believing whatever I told you. You see, to believe or not believe what I tell you is not the point. That's not important, whether you believe it or not. It shouldn't be a matter of belief. You need to be open-minded, otherwise you'll never learn anything new. You need to be skeptical, otherwise you won't know whether what you're experiencing, what you're doing with your mind and your consciousness is real. That means outside of yourself, or whether it's made up That means inside of yourself. So you have to be both. So I don't really want you to believe what I tell you. I want you to consider it. That's the point. I want you to think about it, consider it, and most of all, I hope that you will have an interest to go try to find out, to try to experience it, to make it yours. Because if truth does not come, if your truth does not come from your experience, then it's not your truth. It's somebody else's truth. Okay, so we don't want to get into belief. For instance, some years back there was some books written by Carlos Castaneda, a whole series of them about the Yaqui sorcerer. Then after he died, there was a whole lot of fuss about, was this guy for real? You know, did he really do that or did he just make that up? See, the point is that's not important. It doesn't matter. Read the books. Did you learn something from them? Was there a value to you or not? If there was no value to you, well, does it matter whether he made them up or had the experience? And if there is value to you, does it matter? No. We can learn from fiction. We learn from things called fables, parables. There's all kinds of, there's a wonderful set of Sufi tales that are like parables. Very, very meaningful. Very, very significant little stories. But it doesn't matter whether they're true or not. It matters what they tell you, what you get out of it. So it's the same thing, you know, with this. It's the same thing with everything. Don't ask the question, is this true or is this not true? That's the question of, should I believe it or should I not believe it? You say, it's the wrong question. It's not a matter of believing or not believing it. Think about it. Experiment. Experience. And if you don't have the experience to know, just hold it out there as a possibility. Live with uncertainty. Well, it might be like this. I'm still collecting data. And it might not. I'm still collecting data. You see, that's the way to do it. You have to learn to live graciously with uncertainty. We don't do that very well. Okay, let's talk about a little picture versus a big picture. We're going to get a little more general concept of reality with this discussion. Okay, the big picture is a superset. Little picture then is a subset. I'm going to talk about big picture scientific models. Okay, little picture science has no interest in the subjective. Okay, the subjective, that's meaning, significance, point, purpose, right, wrong, morality. All those things fall under the heading of metaphysics. Okay, big picture models have to describe everything, the objective and the subjective. See, little picture models are only interested in the objective. But we'll find out later there's no such thing as objective. That's an approximation. There is no objective reality. So metaphysics, physics, normal and paranormal, all reality frames and their sources, all of that has to be described and explained in a big picture scientific model. Okay, it has to connect all the dots, fit all the data. To be valuable, big picture science must provide a superset. It must be better physics and it must provide better metaphysics. Okay, and today I'm going to explain, at least we're going to get an intro. Today and tomorrow, I should say, I'm going to explain big picture science. And I'll show you that big picture science derives little picture science, as well as metaphysics. You've probably heard me say that don't confuse the model of reality with reality. Okay, that's a very important point. Little picture science thinks that there is no larger causality. There is no super system. We are the super system. There is nothing that causes us. In fact, physics starts its cosmology with the Big Bang. Okay, when you ask physicists, well, what was before the Big Bang? What caused the Big Bang? You know, who put all that energy in that little spot and held it there and then let it go so it could expand and turn into our universe? And so, you know, what's the causality behind that Big Bang? You will get the answer. None. You know, there is none. It just happened. We start with that. So basically, physical reality kind of sprang out of nothing. There is no causality that we know of. Because if there was, what would that causality be? Where would it be? It would be outside of this physical universe, right? Because it was all that gas that was an energy that was in that little wad that expand. You know, gravity coalesced into suns and, you know, it spread and we ended up with planets and here we are. You know, you go through the evolution of the universe Well, the cause had to be outside of what was caused. You can't cause yourself, you see. A thing cannot cause itself. So whatever the cause was is outside of our physical reality. Okay? Now I make a very simple definition here. You could say, well, it was some other physical reality. Yes, you could, but that's kind of mincing words. It's not this physical reality. Most people, when they think, what's physical? It's this universe. Well, then it's very simple. What's non-physical? It's not this universe. It's outside of this universe. Well, that makes the cause of the Big Bang non-physical from that definition. Okay, so that's just a very simple definition of what's physical and what's not. Actually, we'll find out a little later that physical and non-physical are not really meaningful terms. There really is no distinction that's fundamental between physical and non-physical. Physical is basically your perception. In other words, we are in this reality, so our perception is in this reality. That makes it physical. Right now, we're not dreaming. Well, maybe somebody's dreaming. We got one guy back here dreaming. But most of us aren't dreaming. So we're in this reality. We're not in the dream reality because, okay, this is where we're focused. This is where our attention is. When we are dreaming, we're not in this reality, right? And this reality is non-physical. The dream reality is physical. Physical is not fundamental. This reality is not fundamental. It's just a point of view. And that turns out to be the next level of relativity. Okay, and it follows the same logical formulation of Einstein's relativity. So basically, there is no fundamental reality frame. It's all just relative to the point of view of the observer. All right, models. Talk a little bit about models. Everything, all of our theories, all of our conceptualizations are models. Okay, now scientists often forget that. They begin to believe that their models actually are reality, and that's a mistake. Everything must be a model. So your notion of reality, my notion of reality, scientific, religious notions of reality all represent reality models. Major difference between scientific belief and religious belief is that if you're a scientist, you get to call your beliefs assumptions. Yeah, that's your advantage for all those years of schooling. Okay, but our conceptualizations are just models. Less abstract is don't confuse the map with the territory. Now that's easy, right? We can see that. Here's the map, there's the territory. We can see the map's not the territory, no matter how detailed that map is. Even if that map indicates where every blade of grass is, it's very, very detailed, it's still not the territory. That's simple. Well, that a reality model is not really reality, works the same way. So we asked the question, well, if everything's a model, can we ever get behind the model to experience fundamental reality? And the answer is no, we can't do that. Why not? Because you can't do that unless you can get outside of your reality. Okay, now, we have many levels of reality. Consciousness is the fundamental reality. In order to get outside of consciousness, how are you going to do that? We are consciousness. How do we get outside of the conscious reality? It's a hard thing to do. All we can do is come up with metaphors, descriptions, and models of how it works. We can't get outside of it to see it. Now, this physical reality, this is just this is a subset. Can we get out of this physical reality? Well, of course we can get out of this physical reality. We just have to get into the next bigger superset. But you get to a point where, because we're consciousness, and this is a consciousness construct, and we'll get through all of that, but the idea here is that it's always models because you can't get behind the model without getting out of where you are. You have to get the next level of reality to look back and see your old reality where you were objectively. All right. So you can directly experience the data, but not the source of the data. Okay. We only infer the source. That inference becomes a reality model. Okay. I'm going to go through a little historical perspective here. Albert Einstein in the 1920s, early 1900s, let's put it that way. You don't make a discovery in one day. It takes a long process. But in the early 1900s, came up with relativity theory. Okay, and after that, his next big thing was to come up with unified field theory. Unified field theory was going to be the first scientific theory of everything. And in Einstein's day, what theory of everything meant was all of science being unified under one understanding. And what that meant at a lower level was unifying quantum mechanics with relativity. Because you had two major pieces of science, they didn't seem to connect with each other. One was not derivable from the other. So the assumption was that both were derivable from a more general understanding. That was the toe. That was the theory of everything. Okay? He worked on that for probably 25 years until his death. He was not successful. But he did get to some very interesting conclusions after that much time working on the problem. So we're just going to do a couple of quotes so you can see where did Albert Einstein, who was probably the best scientific mind in the last couple of centuries, a man able to get out of the box, think beyond the limits of science and his culture. Einstein says that there is no space. Okay? Space is an illusion. He said space does not have an independent existence. Reality is merely an illusion, a very persistent one. He says it's clear that the space of physics, that means this 3D space we live in, is not, in the last analysis, anything given in nature or independent of human thought. It's a function of our conceptual scheme. Space is a function of mind. It's a pretty interesting conclusion for Albert Einstein to come to, don't you think? Now, unified field theory needed really just two things that he had to understand how to derive in order to derive his toe. Like I said, it was a matter of combining relativity and quantum mechanics. Okay, so those two things were, for relativity, the key to relativity is the speed of light being constant. Once you understand that the speed of light is constant, then relativity theory is just some algebra. It's logically, falls out logically with mathematics once you understand that the speed of light is constant. And by constant, I mean constant with the motion. What physicists say is that it is a constant. It's invariant with the motion of its source. So if you have a source of light that's moving fast and then you shine light from that source, the fact that it's on this moving, the fact that this flashlight is moving at a 100 miles an hour doesn't speed up the light that then gets shown from that flashlight. It makes no difference. Okay? It always goes the same speed no matter what the source is doing. Well, see, nothing else works that way. Everything else, the velocities are additive. If you're in a car and you're going 10 miles an hour and you reach out the window and you throw a ball another 10 miles an hour in the forward direction of the car, the ball, at least for a few seconds before the wind slows it down, is going 20 miles an hour, right? The velocities add. That was true of everything. So it didn't make sense that light should be different, that the velocities don't add. That was a big problem for physics. It still is. Okay, I'm going to explain to you today why light is a constant. Okay, so that was one thing he needed to know, is to be able to derive that. The other thing he needed to be able to derive was why particles should best be described as probability distributions. Quantum mechanics had come to the realization that particles aren't really massive little particles, they're probability distributions. And why should particles be probability distributions? It's another big mystery. So if he could solve those two things, then he had his toe. And we're going to solve both of those. But you'll see how both of those work. We'll solve that toe. Unified field theory. We'll get to the conclusions. Another physicist, David Bohm, he worked with Einstein, another very high-powered, well-known physicist. Worked in an Ivy League school here in the States, then moved to England, where he spent his last days. Here's a quote from him. He says, "Our notions of consciousness must have room in them to understand what it means for its content to be reality as a whole." In other words, consciousness is fundamental to reality. Okay, reality is a subset. Our reality here is a subset of consciousness, is what he's saying. Okay. Now, Einstein and Bohm both were just stuck. They got to these conclusions a good 10 years before both of them died and left this work. And here's a letter from Albert Einstein kind of expressing his frustration with not being able to find a solution. This was written from Albert Einstein to David Bohm. It was a letter, October 28th, 1954. Okay? It said, one has to find a possibility to avoid the continuum together with space and time altogether. But I have not the slightest idea what kind of elementary concepts could be used in such a theory. Okay? So they knew that consciousness was somehow fundamental, but they didn't know what to do next. They were stuck there. Well, about the same time, but from a very different direction, came quantum mechanics. And quantum mechanics had an even stranger view of reality. Now I'm going to explain quantum mechanics to you. There was a very famous experiment called the double slit experiment, and this experiment defined quantum mechanics. Quantum mechanics really didn't exist before we got to this experiment, and quantum mechanics then came to exist in order to explain what happened here. All right. Light was shown on a barrier that had two slits in it. The light, and this was, decades before Einstein really was even a scientist. This is old physics. Light would shine through these two slits. It's called a diffraction grating. Some of the light would go through this hole because light's a wave, right? Everybody knew light was a wave form. So the wave is just a wave, and it comes up here, and some of the wave goes through here, some of the wave goes through here, and you notice these two lines are different in their length. This one's got to be a little longer than that one, right? Well, when that length was some integral number of wavelengths, in other words, that the difference between those two lengths was one wavelength or two wavelengths or three wavelengths, then the two waves would line up like these two. The two peaks would be together, the two dips would be together. That's called superposition, and you'd get a little spot of light. If you were some integral number of half wavelengths different between these two distances, you'd end up with these two. In other words, the dip would occur at a peak. The dips and peaks would occur. They'd cancel each other out, and you'd get nothing. So you'd have little spots of light here, and then two here, and then one here in the middle, and you'd have blackness between them. Okay, that's just the way waves go together and work. So that had been known a long time. Well, Einstein had done some research in the photoelectric effect, and he had found out that light came in little discrete units of momentum. Well, so do particles. Now, that's a particle characteristic. So we called them photons. And he called them photons. And light was a particle. And of course, as soon as you say light is a particle, and here's the scientific evidence, and he had the evidence, indeed, light did come in discrete little chunks of momentum, there was a problem. Well, light's a wave. How is it that light can be a particle and a wave? So let's do this double slit experiment and see. So they were very clever, and they found a way to send one photon at a time at those double slits. Now, if that's a particle, what should happen? Well, it should go through one slit and hit in a spot right behind the slit, right? Because that's what particles do. Newton told us that. They travel in a straight line unless acted on by some exterior force, external force. That's what particles do. So if it was a particle, it should go through a slit, hit the screen, go through a slit, and hit a screen. It should just get two spots. So that's what they expected when they fired these photons one at a time. But what happened? They didn't get this. They got this diffraction pattern. That was a problem, How is it that you fire this little photon here? It has to go through one slit or the other, right? I mean, it's a particle. And when it does, it picks one of these spots and never goes in these dark spots. Never goes there. What's going on? Well, that was a very big mystery. So they decided that maybe something funny was going on down here at these slits. They wanted to see what was going on with that photon. So they put some detectors. I've got these little red things here. I don't know if you can see that in the back. But these little red things on either side of the slit, those are symbolizing detectors. And they put detectors there to see what the photon was doing. And occasionally, a photon would go through this slit, and they'd detect it. And sure enough, they'd get a spot of light right behind the slit. And sometimes a photon would go through that slit, and sure enough, they'd get that little spot of light right behind the slit, just like they expected. All right, so now they got that pattern. Well, what was the difference? Well, the difference, of course, is that they had the detectors here. The idea was that those detectors were somehow influencing the result. Okay, now for some reason, and I don't know exactly why, it might have been good luck, it might have been clever on their part, but they let those detectors on So the detectors were detecting. Every time a photon went through a slit, the detector detected it, but they didn't collect the data. Now you can imagine how that might happen. Let's say they were collecting the data on a big magnetic tape. Okay? But they just didn't load the tape that day. The tape wasn't in the tape drive. No tape. But the head on that tape drive was still oscillating with, with voltages because the particles, it was still detecting the particles. And what happened then? Well, what happened then was they got this diffraction pattern. And then they could load that tape in the tape drive and measure the data, and they got this pattern. And that now was even a bigger mystery, because it turned out that if you measure these photons at these slits, if you make the measurement, if you collect the data, they're particles. They go straight through and hit right behind the slit. If you don't measure, they're waves, and they create a diffraction pattern. So the act of a conscious person taking the data and bringing that data into this reality made the difference of whether light was a particle or a wave. Well, that was obviously a very big mystery. That confounded all the physicists at the time, and it still confounds all the physicists at this time. Nobody's figured that one out yet. Why is it like that? Well, they came up with a solution, though, how to work with this problem, and I think we'll see that on the next slide. Okay. Here's how they explained it. Well, if you look at the light over here, you'll see that this one's kind of dim, a little brighter, the brightest, dimmer, more dim. So what you have is the intensity of this light kind of goes up to a peak and then comes back down again, right? And that kind of looked like a probability wave, it looked like probability. So a guy named Erwin Schrödinger was a graduate student in Germany at the time, and you will note that most breakthroughs in physics come from young people. And the reason that is true is because young people haven't been in the system long enough to be, to understand what's impossible. They don't know yet that certain things are impossible, so they can think out of the box more easily than the people who've been enculturated into the truth of the physics of the day, right? That's always the case. Well, this young guy was a graduate student, and he said, well, that kind of looks like probability. So let's say that if the photon comes through here, and then it has a certain probability of going to each of these places and a zero probability of going in between, because this looks kind of like a probability distribution. Well, then, all right, let's assume that this photon's really not a particle, but just a probability distribution. Probability, this is the probability distribution here, so that's P for probability, and here's some place, X, some distance, and this probability goes all the way out to plus infinity and all the way out to minus infinity, so there's some probability of where this photon is, right? And some of the probability of this probability distribution goes through this slit, some of that probability goes through here, and the probability waves, as he called them, interacted just like regular waves in that these two distances, if they were an integral number of full wavelengths, you'd get a spot of probability there. You'd get a higher probability there because the two probability waves would superimpose and add to each other, and in here the two probability waves would be destructive of each other and cancel each other out. Okay, so he did that, and of course he got the right answer if particles were probability waves, and at the time the physicists kind of looked at that and they thought, well, what do you expect from graduate students, right? It worked, you got the right answer, but it doesn't make any sense. It doesn't mean anything. Particles are probability, what does that mean? Well, what happened next was that they took this idea of this crazy graduate student and they applied it to other such problems of particle physics. And what did they find out? It worked there too. And it kept working. And the more they brought this theory along and expanded it, the better it worked. So because it worked, they had if you will, a mathematical formalism that would predict the correct answers. And quantum mechanics today is one of the most successful branches of science ever. It's very good at predicting what happens in experiments. Okay? When you can predict what happens in experiments, people tend to believe that that's the way the world works. Well, what happened then was that physicists decided that they needed to interpret what did this mean. What does it mean that we assume that particles are probability distributions? I don't mean that there is a probability that the particle is somewhere. The particle is somewhere, and here's its distribution. Okay? It means that the particle is itself a probability distribution. There is no particle. It's just probability. See, now how do we interpret that to make sense in our world? Well, that physicists now have spent almost 100 years worrying over interpretations. There is no interpretation. It's just a fact. All particles, and it's not just at the microscopic level, it's at this level too. Everything is in probability. Everything is a probability distribution before the measurement is made. And what happened is when you make a measurement, and what physicists will say is that the measurement collapses the wave function to a physical particle. That's the way a physicist would put that. Okay, so you make the measurement. In that case, it was measuring at the detector. When they measured a particle here, they got a particle, and the particle then acted like a particle. They didn't measure a particle. There was no particle, because it's the measurement that collapses the wave function to a physical result. There is no physical result. It just stays probability, passes through the two slits as probability, and produces this pattern. All right, that was the explanation. Still the explanation today. Now, some physicists went to the point of saying that consciousness causes the collapse of the wave function. That's not exactly true. It's not that consciousness causes it. Indirectly, that is true. You can't take a measurement without consciousness. You know, the equipment doesn't take measurements itself. It takes a consciousness to take a measurement. So indirectly, consciousness does cause the collapse. But directly, what causes the collapse is taking the data. It's the measurement that causes collapse. Okay, that's the direct cause of it. It's the act of recording that data. Another way to look at it is that photons, particles, are created by a consciousness measuring them. But it's the act of measurement that creates these particles. We're going to see this act of measurement creates everything. Our whole reality is created this way. You see, physicists will tell you that quantum mechanics only applies to little tiny subatomic particles. Now, I just talked about photons, but they've repeated this experiment with electrons, which is a massy particle. They've repeated it with whole atoms. They can put hydrogen atoms, does the same thing. Any particle works the same way. Okay, but they will tell you it's just as tiny little particles is all it applies to, but it doesn't. We'll see later that it makes sense. Our whole reality works exactly like that. Everything in this reality is probability before the measurement's made. Okay, now I know that doesn't make any sense to you right now, but it will make sense to you by the time we get to this time tomorrow. Okay, I got a couple of more quotes, this time from the quantum mechanics guys instead of the relativity guys. This is from Eugene Wigner. He was one of the primary developers of quantum mechanics, has a Nobel Prize for his work. He says, it will remain remarkable that whatever way our future concepts may develop, the very study of the external world led to the scientific conclusion that the content of the consciousness is the ultimate universal reality. Max Planck, known as the father of quantum mechanics, though he did not invent it, he did do an awful lot of work in it that extended it. He says, science cannot solve the ultimate mystery of nature because in the last analysis, we ourselves are a part of the mystery we're trying to solve. That sounds a lot like Einstein, doesn't it? The space of physics is a function of our conceptual scheme. What's out there is entangled with what's in here, okay? Now, we're talking about basic physics here. This is not just, some ragtag bunch of New Agers, came up to these conclusions. This is solid, accepted, everyday physics. This is the way reality works. Okay. All right. So the giants of physics theory come to some unsettling conclusions. If you look here, I have these yellow lines. The ones above the yellow line were basically came from the relativity side from Einstein and Bohm. The ones here, both of them agreed on, well, both. The other group is the people, these came from the quantum mechanics, the quantum mechanics group. Okay, so this is quantum mechanics, this is Einstein and Bohm, and everybody said the same thing here. All right, so basically, space and time being continuous is a problem. Physical reality is an illusion, doesn't exist independent. It's a mental construct. The relationship between physical reality and consciousness is fundamental, but it's unknown. They knew the traditional assumptions were wrong. but they didn't know what to do about it. They didn't know how to take the next step. Okay, they all agreed that consciousness is somehow at the root of reality. The quantum mechanics guy says that reality is neither objective or deterministic, it's statistical, it's based on probability, and that reality mass exists only as a probability until a measurement is made. Now you think that was back in the 1920s. Well, where are we today with this? You'd think a lot of progress would be made since the 1920s. Actually, I think it's probably more likely we've regressed rather than progressed. And that's because, actually, if you read these statements today, there'd probably be a lot of physicists that would look at that and say, oh, I don't think so. That's probably not true. That's just some science writer's idea, way it worked. But no, this is physics, and this is actually the real Einstein, and he did say these things, and this is fundamental physics. What happened is that when you get to a point where you hit the wall, where you can't take the next step, you just don't want to do next, well, if you have a career, you go away from that and you do something else. Okay, now Einstein and Bohm banged their head against that wall for 25 years and didn't make a dent in it. So that didn't make other people feel like there was there was a lot of career building prospects there. So basically physicists backed away from these understandings and kind of say, well, let's not go there. Let's not work that problem. We'll just call that the measurement problem and we'll forget about it. And if you tell a physicist, what's the measurement problem? He'll tell you, well, why is it a problem? It's a problem because nobody knows, what to do about it. It's a big mystery. That's why it's the measurement problem. So there's not a lot of work or research or anything else trying to discover, take that the next step. Finish Einstein's work. Nobody goes there because it doesn't pay. All right, why did they hit the wall? Okay, continuous solutions are not the right answer. Reality, space and time comes in discrete units. It's digital. Okay, now by digital, I mean that it comes in chunks. It's not continuous. That's what I mean by the word discrete. Discrete is another word for that. Okay, now we'll see in a few slides from now that there is a group of physicists now called digital physicists who do start with that idea. See, everything else we found in our reality is discrete. Everything. If you get this lectern or those tables that are in front of you down to a molecular and then an atomic scale, what do you have? You have discrete particles. It's not this continuous piece of metal that you see here. It's discrete particles with lots of space between them. That's what this is all made of. So when you get down to the lowest level of anything that we know of, it's discrete. And the only two things that we don't put in that basket of being discrete particles is space and time. Well, that's because we can't measure that accurately. Okay, quantum mechanics has a length called the Planck length. It's about 10 to the minus 36 meters. That's where Planck said that space becomes granular, starts to break up into pieces. But then physicists didn't know what to do with that either, so that just kind of sits there and nobody does anything with it. Okay, but that's too small for us to measure. 10 to the minus 36 meters is a very tiny, tiny measurement, and we cannot measure things that small. So it seems continuous to us, where we can measure atoms and we can measure the effects of molecules. We can't measure effects of the granular space. So that's one thing. Space is not continuous. It's digital. It's discrete. Same with time. Time is not continuous. It comes in little delta t's, little chunks. And we'll explain that to you. Okay, they expected the physical reality was going to be fundamental, and this reality is not fundamental. This reality is a subset. There is a superset. There's something more fundamental than this. This is derivative. Okay, they didn't understand that. So they weren't looking for the superset. They wanted to find the answer here. Well, you cannot find the superset by looking at the data in the subset. The subset doesn't contain the information to describe the superset. Now that's like, third grade logic, right? You can kind of understand that. The subset doesn't contain the superset. The subset is just a subset of the superset. Okay, so if you're just looking in the subset for the superset, you can't find it. So that was another one of their problems. They were looking for something that was objective and deterministic. Our reality is not objective, and it's not deterministic. It's statistical and subjective. And I'll show you that by the end of the day tomorrow too. Okay, the appearance of objectivity, as it turns out, is only an approximation. Okay, consciousness is at the core of our reality is subjective. Consciousness is fundamental and personal. It has to be experienced from the inside. That all hard science is objective is what I call a scientific belief. Just like that we existed from, our physical reality came from a big bang that had no cause. That's a scientific belief. Okay, it's not falsifiable. It's just a belief. Okay, we're going to apply quantum mechanics to the larger reality. First, let me try to explain to you why there is no such thing as objectivity. If we measure something big, let's say like the sun, we're going to measure the sun. Well, how do we measure the sun? We take measurements and we get its mass, its size, its pressure, its temperature. But those things are all changing. Millisecond to millisecond, the size, temperature, pressure are all different. So how do you measure the sun? Well, you measure statistically. Its size is, from here to here, plus or minus this is statistical. Well, that makes sense, right? It's big, it's all constantly changing. The only way to describe that is statistically. It's mostly about like this, or the probability of it being this mass or this diameter on any particular moment is this, okay? Now, what about something then that's not quite so changeable? Well, what is the most unchangeable thing you can think of? And I thought of that, what came to my mind was a brick. Okay, think of a brick, concrete block, a rock, any of those things. Okay, but brick is nice because it has a nice defined shape. So let's look at that brick. How long is that brick? Well, we get a measuring tape out and we'll say, oh, it's 8 inches. But that's only an approximate answer. It's not really 8 inches, is it? We look down at it in detail. We look at the end of that brick, and it's not a smooth surface. It's real bumpy. There's valleys and hills and peaks, and there's a topology to the side of that brick. Now, at our scale, it looks smooth, but on a molecular scale, it's really, really bumpy. And then we get down even smaller. Besides the topology bumps, we get to look at the molecules themselves. Well, molecules aren't standing still. Those little molecules are in there dancing all around. They don't stand still till you get the temperature down to absolute zero, and that's something that you can't do. So they're always moving. Well, now how long is that brick? How can you tell how long it is? Well, let's say you give that brick to 100 physicists, scientists, you tell them to go measure that brick. They'll look at it, and there's some peaks and valleys, and they'll say, well, let's take an average of the peaks and valleys. Or someone might say, well, let's just go to the peaks, peak to peak, or valley to valley, or take an average, and what you get, even if you decide on what the process is, you'll end up, if you have 100 physicists measuring bricks, you'll get 100 answers and they'll all be different. Matter of fact, you get the same physicist measuring brick twice and you'll get 2 different answers because there's variation in the equipment, right? The equipment they use to measure it is different. It's changing. It's moving. It's not still either. So you get 100 different measurements. Well, most of the measurements would be right in here. There'd be a few out here on the short side. There'd be a few out here on the long side. And what would you end up with? Probability distribution. So how big is a brick? It's probability. It's statistical, just like the sun. The brick's always changing. And if you think about it, everything is like that. There is nothing that is objective. All things are just statistical. What exists, what its extent, anything you can measure has measurement error. Okay? And that's not only because you're measuring, you have measurement error because your tools have error. Your tools are all, they measure to this accuracy, plus or minus, right? And that plus or minus is the error. Plus you have the human error of applying the tool, plus or minus a certain amount of error. Plus you have the actual physical thing itself is in motion at the molecular and atomic level, and that produces error. Everything is just statistical. Okay, in fact, reality is statistical at a much more fundamental level than just measurement error. A future sun, like everything else, a future brick, a future atom, a future photon, a future statistical analysis, exists only in probability and is brought into this reality frame by measurement. Okay? The result of a particular measurement is randomly sampled from the array of discrete possible states that represent the probable future of that object at that instant. Okay? That's how it's done. However, once the measurement's made, okay, there's a few things that have to happen. One, that measurement must fall within the natural uncertainty of the data, object, or process. In other words, that brick is certain length, plus or minus, say, 1,000th of an inch. You know, that's because of the manufacturing process, has that error in it. So you're not going to get an error when these physicists measure the brick, say, oh, the brick is 2 feet long, or the brick is, you know, 1/2 inch longer and all the rest. That goes outside of the bounds of the natural area associated with the object. So it has to be inside the natural error. 2, you have to maintain historical continuity. Okay? You can't measure something and then have it change. You know, history has to be continuous and it has to have consistency. You can't go out here and say, well, there's a great forest out here of conifers, you know, it's all pine trees, and go back the next day and they're all deciduous, you know, with leaves. You can't do that. That violates history being continuous. Okay, so the history has to be maintained. And the last thing is that it has to abide by the rule set of our causality. Well, what is the rule set of our causality? The rule set of our causality is physics, science. Science digs out the rules of how this reality we're in works, right? That's the rule set. But that's not all the rules. There's some rules that science hasn't found yet, of course. So there's a larger rule set. Actually, I gave you 3 things: that they have to fall in the natural uncertainty of the data of the object, they have to be historically consistent, and they have to fall within the rule set, right? So you can't have that brick suddenly becoming 2 feet long, or the brick turning into a block of cheese or something like that. You know, that violates history, it violates the rule set. You know, those things can't happen. Okay, but there's actually only 2 conditions. The first condition about the natural uncertainty, that is derived from the fact that history has to be continuous and that you have to abide by the rule set. Those are what create that plus or minus error that has to do with the measurement error. Okay, so there's really only 2 conditions. I broke out into 3 because it's easier to see it that way. We're going to see that quantum mechanics, that reality is based upon probabilities, not only true for the very small, but that it applies to the macro world as well. It's a general principle. Okay? It affects our reality at all levels and at all scales. Okay, the objective world is another one of those scientific beliefs. I have 2 things I'd like to define for you, and one of those is decision space. We're shifting gears a little bit, but it's really a part of the same subject. Decision space, everyone has their own personal decision space. Okay, now decision space is basically a list of all the decisions that you can make. Now, it's just the ones that you know about that you can make. There are some decisions that you can make that you don't necessarily know about, right? They're outside of your reality. But you could make those decisions. They're just not you just haven't thought of them, right? They're not in your reality. They don't count. It's not all the decisions that you could possibly make. It's all the decisions that you could make at this particular time. So now your decision space gets smaller and gets bigger based on whether your reality gets smaller or gets bigger. So that's the decision space, and we all have a different decision space. Somebody throws you in jail and your decision space shrinks in some ways, because if you feel like going home to mama, you can't, right? You're stuck. So there's some decisions now that you used to be able to make that you can't make any longer, okay? So your decision space changes. So that's decision space. Now, the reason I define that, and the reason it's important, is because that's a key idea to understand free will. Free will is the freedom to choose one of those decisions in your decision space. Okay, that's what free will is. I have some people who want to argue about free will that somehow have the idea that free will is having a genie with unlimited wishes. You know, it's that you get everything that you want. That is not free will. And the example that I got, I was on a radio interview, and the host of that radio interview didn't, I think, really believe that we have free will. And her argument was, she says, well, just imagine now you're a little child, you're a toddler in the back seat of a car, and you got one of these little child seats with a steering wheel on it, so you can pretend that you're steering. Right? You've seen car seats like that with a little steering wheel on them. And at the little child sitting in the car seat, grabbing hold of that wheel, and the little child wants to take a right-hand turn and go to the park. So the little child turns the wheel, but mom has other ideas. She turns left and goes the other way. And then the radio host said, you know, does that little child have free will? And I'm thinking, well, of course she has free will. That decision was not in her decision space. She couldn't make that decision, right? That was mom's decision because mom was driving a real car. Okay, so it has nothing to do with free will. Free will doesn't mean getting everything you want. Now, of course, the analogy there was that we, as people, are like that. We're like the little kid in the backseat grabbing hold of. We think we're in charge. See, we think we're driving the car with our little steering wheel, and we're really not. You know, fate takes us to the left when we want to go to the right. You know, we have jobs that we wish we didn't have that we could change. You know, we have all kinds of things, and they say, well, you know, if I had free will, you know, I wouldn't be in this mess. You know, I'd do something else. Well, free will is not having a genie with unlimited wishes. It's just a matter of being able to pick from the decisions that are in your decision space. That's what you have the free will to do. That's it. Okay, so that's a very precise definition of free will. Now, of course, if there's no objective reality, then you can't have any determinism either. Determinism requires objectivity. How can you have determinism when everything in it is moving around and changing and you can't pin anything down? Well, let's talk about determinism. There is uncertainty within choice, and there's uncertainty within interaction. So this is like, let's talk about randomness among sentient entities, okay? Because we're going to have two different flavors of determinism here and two different flavors of objectivity. One has to do with people, and then one has to do with things. So with people, there's uncertainty within choice. Okay, you have these choices in your decision space, and there's uncertainty about which one you're going to choose. You're not quite sure why. Do I pick A, B, or C? Do I go through the red door, the blue door, or the white door? So you have uncertainty with your choices, and then, of course, with your interactions, how you interact with something. It's your choice. See, that little girl in the back seat, what was in her decision space was whether to cry and scream when the car went left and she wanted to go right or not. See, that was in her decision space. She could decide whether to pitch a fit or whether to just go with the way the car went and be happy about it. So, that's something she could choose. But whether it went left or right, she couldn't. So how we interact with things. Okay, what happens is that complex interactions produce what I call practical randomness. Now, a mathematician will get into a very theoretical randomness. What is perfectly random? And we don't care about that. That's not an issue. Practical randomness is good enough. I call it social Brownian motion. I don't know if Brownian motion rings any bells with you when you were in high school science, but Brownian motion had a bunch of particles in a box, and the particles all run into each other. They all bump and hit, so any one particle might be bounced up or down or back or sideways, and you let these things all bounce around, and what you have then is a random distribution of the particles because they're all bumping into each other, and it was called Brownian motion. Well, what we have is like social Brownian motion. Doesn't that sound like our lives? We bump into things, we bump into this, we bump into that, we meet these people or those people, or things happen, our house burns down, whatever it is. All this stuff, we bump here and we bump there, and all of those bumps take us to where we are right now, So it's kind of there's a lot of practical randomness because we are a free will, choosing among the things in our decision space, interacting with a lot of other people with free will, choosing among the things in their decision space, and that is an interact. Sometimes it's a clash. Sometimes it's not. But that is like Brownian motion. You get bumped here, you get bumped there, and that presents practical randomness enough to provide one's decision space with a constantly changing, rich array of choice for the free will to select from. Okay? So that's plenty of randomness for your free will to select from. Now, among objects, like we were talking about bricks and suns, randomness is intrinsic. Okay, given initial conditions, it's a scientific theory. Actually, it's a scientific belief that one can predict a particle's behavior deterministically. Now, if you had a box of hydrogen atoms, a box of particles again, if you had a box of hydrogen atoms, say, most physicists would tell you that if they knew exactly what the initial conditions were of any one of those hydrogen atoms, they could tell you where it would be any time later. right? Or if they knew the initial condition, if there was only one in the box, they could tell you where it would be any time later. If there's a whole bunch of them in the box, if they knew all the initial conditions, you know, the velocity, the location, you know, everything, then they could tell you where it would be. Well, of course, that's a fantasy, right? Because you can't have an initial condition that accurately. Your initial condition has error. So you can't specify something. You can't know what that initial condition is because you can only know it to the degree that you can measure it. So right away, you can't set it. Secondly, when that particle hits the wall, it's not a flat wall. It's full of molecules. And what are those molecules doing? They're dancing, they're jumping around, they're moving, and how that thing interacts and moves, it's random. So you cannot deterministically determine given initial conditions in the real world. Okay? Now, if you're in a make-believe world where everything is still, where there is no jiggling, where you know to infinite precision, you know, where everything is, in that make-believe world, determinism exists. But you know, in make-believe worlds, you can dance with an elephant in a blue tutu, right? Anything can happen in a make-believe world. In a make-believe world, I can flap my arms and fly. But that doesn't have anything to do with science. Now, does it? Well, neither does objectivity or determinism. It really doesn't have anything to do with science. So what you end up with is you find out that objectivity and determinism exist only in the limit. They exist only as an approximation. Okay, sometimes they're approximately objective and it's approximately deterministic. Some simple cases. Okay, so think of the real world as statistical. Okay, but an approximation that it is objective is sometimes not that bad. But you have to remember it's an approximation. And you see most physicists miss that point and they believe they live in an objective reality. They don't. And we'll see that there's lots of places where that objectivity fails because the approximation isn't good. Well, one of those places was in that double slit experiment, wasn't it? You see, it didn't, that approximation didn't hold true there, and we'll see it doesn't hold true lots of places. And in understanding that fact, we'll be able to understand a lot about reality. And we will solve a lot of problems and be able to explain things that otherwise are not explainable. You know, an example of how that works is that if you take, you know, there's a theory called the kinetic theory of gases, which explains pressure and temperature and that kind of stuff based on statistics of how the atoms bounce around in the box. Well, they will tell you that under any initial conditions, whether you put those atoms in that box by putting them in a stream that's just horizontal, it takes only microseconds before you have a random distribution inside the box. In other words, the uncertainty scrambles the answer almost instantly. So that's just also basic physics. Okay, we have to compare this with kind of the history of science. Tells us that this is how we step up. Okay, want to step up in our concepts. Once upon a time, we thought the Earth was flat, right? And then we found out it wasn't. But when we found out it wasn't flat, we realized that flat was really a good approximation for short distances. As long as you were only going short distances, flat was all right. If you're going long distances, you know, if you were doing your geometry or you were doing your surveying over long distances, flat didn't work anymore. But it was a good approximation under short distances. Well, then we got to the point where we found out that we weren't the center of the universe, you know, and that our solar system had a sun, and that was a better description of putting the sun at the center of our solar system. We discovered gravity, and suddenly we had Newtonian mechanics, right? And when we had Newtonian mechanics, we thought, of course, that we knew everything. You know, the universe was a big clock. You know, it was all clockwork. It was, you could just calculate everything. And then came along quantum mechanics and relativity. And guess what? Newton mechanics didn't work anymore. Well, what happened to them? They still work, but they're just approximations. They work inside their own limited area, okay, where the speeds aren't too fast and the sizes aren't too small. Newtonian physics works fine. So you see, this is kind of the trend. When you get the bigger picture, the littler picture that you had before becomes an approximation. You see? You realize that the little picture, it's not that the little picture was just totally wrong and, it was a bad idea. It's that you just had a smaller picture. And at that little, the ideas you had there, yeah, they do work and they still do hold true, but only in the limited area, where they kind of belong, where they were discovered and where they belong. Well, we're going to see the same thing. Now we're looking at objectivity and determinism are just special cases. They're just true some of the time. They're a subset. There's a bigger, larger superset that explains reality, to which the old physics and the old determinism and so on becomes a subset, okay? Just a limited subset, all right? This slide, all the art that's in my presentation, were all done by Judy Johnson. You saw a picture of Einstein and a picture of me in there and so on. And Judy came to the workshop when we did the very first one, and it was about a year and a half ago. And she took me aside later and she says, "Tom, your charts are visually boring. You need something to spiff them up." So she's an artist and a very good artist. So she drew these cartoons and she drew all the pictures to spiff my slides up a little bit. Now I'm not going to ruin the joke by trying to, if you can't read it, that'll give you good incentive to download the slides. I didn't tell you that in the beginning, but all of these slides, you can go to www.mybigtoe.com, and right on the front page you'll find the New York slides and you can download them. They're in a PDF format. But I wouldn't print them in color if I were you. It's going to take a long time and be expensive. Black and white's probably good enough. But anyhow, the slides are all there. So you can read this joke if you can't read it. The point is of the joke, though, is that that's Bohm and Einstein. You can obviously tell Einstein. He's with the bushy hair there and the little mustache. The point is that Bohm and Einstein did not have the necessary concepts within their reality to go any further. You see, there was no, back in the 1920s or even the 30s or 40s or 50s when they wrote that letter, there was no digital science. Virtual reality didn't exist. We have virtual reality games now all over the place, right? We can't drag our kids away from them. Right? Virtual reality is here. So information science has been here now for a while. Okay. The paranormal research that's gone on. We have real hard science research that shows the entanglement between mind and matter. Even simple things like the placebo effect, entanglement between mind and matter. That wasn't really available. So all of those things were really outside of their reality frame. That's why Einstein and Bohm couldn't take that next step. But we can do better, and we are going to do better